to talk about rings, and will, I think, be still quite elementary, mostly just introducing some relatively standard words. And so let me introduce, so I have introduced rings and some examples and some properties like commutative, and now I introduce a few more rings, a few more properties. So some further properties, for instance, further properties of rings. So one property which is very useful is that one doesn't have zero divisors. So if two elements are non-zero and one multiplies them, one doesn't get zero unless one of them is. And so that's like in the integers. And so that R being a commutative ring with 1, I only consider it in that case. I don't know why I need 1, but anyway, a commutative ring. So an element A in R is called a zero divisor if there exists an element B in R which is not zero, such that A times B is equal to 0. I mean, it's straightforward to check from the definitions that the multiplication with 0 will always give 0. No, that's an exercise. Okay, it's also in the notes. And so in particular, a commutative ring with 1, which has no zero divisors, behaves a bit like the integers, and so we call it an integral domain. And our standard example of an integral domain would be the integers. There.
The definition is different from C.
What? Yeah, that otherwise that wouldn't have made sense. Yes. Obviously, I mean we don't want to print a so. Yeah, a zero divisor is a non-zero element. That's correct. Otherwise, that would be not such a great definition because there would be no integral domain, which would not really be so great. So, as an example, as I said, Z is an integral domain. And if I take Z6, this is not an integral domain. Because the multiplication in this ring is just multiplying and then taking the rest. So if I take 2 times 3 is equal to 0. And on the other hand, if P is a prime, then the P is an integral domain. Because if I have two integers which are not divisible by p, then also the product will not be divisible by p. And so the rest, after dividing by p, is not zero. So these are some simple examples. And in an integral domain we have the cancellation. So if R is an integral domain, and we have some elements, and we have, let's say, A, B. So if AB is equal to AC, with A different from 0, then it follows that B is equal to C, and that's clear because this says that A times B minus C is equal to 0, and A is not 0, so therefore B minus C must be equal to 0. Okay. We have introduced the unit element. So a ring can have some invertible elements so that the multiplicative inverse exists, and the set of all invertible elements are called the units, and they themselves form a group with multiplication. So let R be a unit of the ring. Now I want to mutative an element A in R is called a unit if it has a multiplicative inverse. So if there exists an element B in R with, say, AB is equal to BA is equal to 1. And so the set of units in R is usually noted R star and called the multiplicative group of R. In fact, can easily check that if I take the units with the multiplication, this is a group. I mean, we have this, so there's not very much to see. We know the multiplication is associative. We know that 1 is in R star is a neutral element, and if A is a unit, also A to the minus 1 is an element, and if A and B have an inverse, then also the product of A and B has the inverse, namely the product of the inverse of A and B the other way around. I mean, as before, so for if A in R star also A to the minus 1 in R star, and they take if A and B in R star, then A B to the minus 1 is equal to E to the minus 1, E to the minus 1. And so we have an image. Okay, so this is trivial. We can look at a few examples. So the multiplicative group can be much smaller than the ring itself. For instance, if I take the units in Z, this is just 1 and minus 1. If I take the units in the ring of Gaussian integers, one can check as an exercise that this is just 1, minus 1, 9, minus I. And well, you all know the non-commutative example, if we take, say, the 2 by 2 matrices with coefficients in R, and the units in this are just those which have determined non-zero. So A, B, C, D. Instead, A, P minus P. Not zero. So then the matrix is inverted. And so okay, so this was something very simple. Now I want to introduce something which you are also very familiar with, only in slightly bigger generality, namely polynomials. So polynomial rings. So everybody is familiar already from school of polynomials. And but we make slightly more generally polynomials with coefficients in a ring. And we want to define them a bit more abstractly. And it is, in spite of the fact that it's a quite simple thing, it's very useful because it allows us, to construct bigger rings out of smaller rings and study them. And so, so here I will assume that R that R is a ring with 1, so a unitary ring. And at least I find it better that way. So a polynomial so it's f with coefficients in R. This is a formal sum. So like we had it for the group ring, f equal to a0 plus a1 x to the 1 plus 1 plus an x to the n, or I can write it out I equals 0 to n ai. So maybe make it consistent with x to the 0, ai x to the I, where the ai elements in R. But this is only, so formal sum just means it is given by this tuple of numbers. No? We have just these n numbers. But there's a tiny difference. If two such things are equal, if the first few of these coefficients are equal and the other one, if you have two polynomials f and g and they have the same coefficients except that one has more and these are all 0, they are considered to be the same. And we don't have to write so two polynomials. So f equal sum I equals 0. M ai x to the I and g 0 to n bi, or maybe I call it j, bj, x to the j are called equal. And we just write f is equal to g. If so, assume for simplicity, so g m is smaller equal to n, otherwise it would be the other way around. So if ai is equal to bi for 0 smaller equal to I smaller equal to m, and bj is equal to 0 for m plus 1 is more than equal to j is more than equal to n. Okay. So you could view this, if you want to be very abstract, you could say that the polynomial is actually just a sequence of numbers where two such sequences are identified if all the coefficients, well, no, I mean, then it's just a sequence of numbers, but that one with the property that after a certain point all coefficients are 0. But it's somehow maybe easier to think of it in this form. That's also much closer to what you are used to. And so one thing I should say, it's important for this algebraic stuff. So in school or whatever, the polynomial is actually a function. So you view it as a map. So we will later do that, but it's not what for us polynomial is. Polynomial is for us this expression, and that's it. So normally, if you're in school, it's a function. So you want to put something for x, and the polynomial is determined by this function. It's just the function given by this expression. But here, in Aurora, it's just this formal expression. And for instance, if r is very, very small, then this makes a difference, as we will see in a moment, because there can be many more polynomials than there are functions. And if anything, and that's how we use it later, you want to view a polynomial as a function on any ring of which R is a subring. So it's it's not just one function but many functions. And so therefore it's not just determined by as a map. It's not a map given as a map from R to R. I mean, that's not how we view it. So let's just go on. So we denote Rx the set of polynomials with coefficients in R. And so we identify A0 in R with the polynomial A0 times x to the 0. So for us this is the same thing. We just don't write this, we somehow think that x to 0 is equal to 1. And so with this, we have that R is a subset of Rx. And a polynomial of this form, so this is a constant polynomial. Okay, so these are all just things. And now, I wanted to say this thing which I already said earlier, but maybe you could still write it down. Namely, this is this remark. If I have polynomial f in Rx, this defines a function which I could also call f from R to R, which sends an element b to what one could call f of b, which is, if I write f equals sum I to 0 to n ai x to the I, where I just replace okay, that's an element in b. So it defines a function, and that's very important, but it is not equal to the function because, but it is not that function. So, for instance, R is Z2, then obviously if you take Z2 of X, this contains infinitely many polynomials. But there are only 4, I think, maps from Z2 to Z2. Okay. So therefore, if I view it as a function, all of them get identified into these 4 classes, but we don't want to do that. Okay. Now, obviously, we want this to be a ring, so we have to define the ring structure. So the addition is just component-wise, as you would imagine, and the multiplication we do by kind of formally multiplying out, saying that x to the I times x to the j is equal to x to the I plus j, and then applying the distributive law. And this gives us a formula. So the ring structure is for f, say, equal to sum I equals 0, and ai x to the I, and g equal to sum I equals 0 to, I can take the same n, because I now can add zeros, di x to the I can define f plus g is defined to be as the same sum of, and I just add the coefficients. More interesting is the product. So I first write it out. This is the sum I equal 0 to n. Sum over all j plus k is equal to I, aj plus bk times x to the I. So I wrote it now in this form to see directly that it's a polynomial, but obviously what you just do is you say a x to the I times b x to the j is equal to ab x to the I plus j, and require the distributive law. For this sum. And this gives me these formulas. And yeah, okay. So now with this, it's easy to check. I don't do the details, so you can position. So you can check easy. Check that Rx is a unitary ring. If R was a unitary ring, obviously the unit element is the one in R. So, viewed as a constant polynomial, and the zero element is 0 in R. So R is a subring of Rx, obviously, because this is, if you multiply two constants, will be a constant. And if Rx if R is commutative. And so this Rx. Okay, so we have this way of making this bigger ring out of a smaller one. So now we want to see, which is also not very difficult, but we want to see that if R is an integral domain, then also Rx is an integral domain. And this also, for this we also need to introduce the degree of a polynomial. So definition. So maybe first, obviously we don't always want to write all this nonsense here, so we use the standard notation. So usually drop 0 coefficients. So if some of these numbers is 0, we don't necessarily have to write it. So we can, for instance, write x to the 4 plus whatever 5x plus 7 instead of what is it, 7 times x to the 0 plus 5x to the 1 plus 0x squared plus 0x to the 3 plus 1 times x to the 4. Okay? You just write it in standard.
The multiplication, the sum is from 0 to...
What?
In the multiplication, the summation is from 0 to n?
To 2n. But it should have been 2n. I don't know why I didn't write it. But, obviously, it's... okay. So, so the degree of polynomial is just the highest power of x where the coefficient is non-zero, so that we can write like this. So if f equals sum a I equals 0 and ai x to the I with ai different from 0, then then the degree of f is n, and an will be the leading coefficient, an, and an is called the leading coefficient. And with this, we can easily see that the polynomial ring with coefficients in an integral domain is an integral domain. This is also remarked. So let R be an integral domain. So, and we take two non-zero polynomials. Then first f times g is non-zero, and in fact the degree the degree of f times g is equal to the degree of f plus the degree of g. Well, Rx is an integral domain. And I don't know what else. And you can also see, I don't think for this I need the integral domain, but anyway, that if I take the units in Rx, these are just the units. In R, so only constant polynomials can be units. So there's not much there. So we take such polynomials so that f, you just write it out, I equals 0 to n a x to the I, g equal some I equal whatever, j equals 0 to m, bj x to the j, where this is actually the degree. So a n is different from 0, and so is dm. Then if what is f times g? This will be somehow according to our definition. This is the sum of all k from 0 to n plus m over ck x to the k, where ck is the sum of all I plus j adding up to k of ai times bj. Now, so the highest we can get is n plus m, and on the other hand, what is the coefficient of n plus m? If we look here, this whole sum consists only of one summand, namely here we have ai, an, bn. So we have c n plus m is equal to an bn. And as these are both non-zero, this is not zero. And so this shows that f times g is not 0, and its degree is n plus m, which is the degree of f plus the degree of g. And obviously 2 is just a reformulation of this statement. You have if you have two non-zero elements, the product is non-zero. Okay, and then the last one is just a simple fact, but again using the degree. So if f is a unit in R, then f is also a unit in Rx, because I can just take its inverse in R as inverse. So we only have to see the other one. So let f be a unit in Rx. So then it has an inverse. So then there exists a g in Rx with f g is equal to 1. But we have seen that the degree is additive. So it follows that the degree of f g, which is equal to the degree of f plus the degree of g, is equal to the degree of the constant polynomial 1, which is 0. So therefore, as the degree of a non-zero polynomial is always non-negative, it follows that both these numbers must be 0. And have degree 0 means precise to be constant, so that means f and g are both elements in R, and f and one is inverse to the other, so it follows that f is. Okay. So this shows at least that this degree is a useful. Yes?
What is the degree of zero polynomial?
Well, that's so one can have different. That's a question of convention. So one could either say it doesn't have a degree, or one could say the degree is -1, because that's useful in some computation, or one could say it's -infinity. That's also sometimes useful. But at any rate, sometimes you want something like the degree adds up in certain calculations, and then it might be useful to have it either -1 or -infinity. But a priori, the way I've defined it now, the zero polynomial has no degree. That's in the moment how I view it. But you know, if you look at in the literature, you find different conventions, you know, each of which has some advantage. So I also briefly want to talk about division rings and fields. So I will not be really interested in division rings, but at least give me one example. So if I have a ring with a unitary ring, is called a division ring. If the units in the ring is the same as R without 0. So every element which is not 0 is a unit. It's clear from the definition, we know whenever we multiply anything by 0, we get 0, so 0 can never be a unit, so this is as large as it can possibly be. So every non-zero element is invertible. I want to at least and then commutative division ring is called a field. Now we will not be interested in this, but at least I want to mention it. The theory of fields is maybe the main topic of this course, so therefore we will talk about this quite a bit. But briefly I can at least give you one example of a division ring which is not a field, which is the standard example, the quaternions. So examples. So this I H after Hamilton, who invented them. So these are somehow 4 tuples of real numbers. So we have A plus, so we have the symbol I plus C, J plus D, K, where these I, J, and K are just symbols. So we have the coefficient, the variables are A, B, C, D, where A, B, C, D, and R. So the addition is just, so this is just another form of saying it's R to the 4. It's only that I've labeled this one by 1, this by I, this by J, this by K. And the addition is component-wise. So just if I have A1 plus B1I and so on, and the same for 2, then we have A1 plus B1, A1 plus A2, B1 plus B2I, and so on. That's okay. And then the multiplication is a bit, I just write it very briefly. So multiplication is defined by formally applying the distributive law. So if we have two such factors, we treat them as if this was not just formal, but this was an actual sum of things, and then we multiply it out by the distributive law, and requiring, I write it in a slightly shorter way, which is a bit implicit. So the square of any of these things should be equal to -1. And if I multiply all 3 of them together, this should also be -1. And if you apply this in some way you can deduce all relations from this. So this is a nice, assuming that the multiplication is also associative. So we assume also associativity, and we have these rules, and this defines the multiplication. Because by just saying that we formally multiply this out, and then if we encounter a product of these IJKs, we use this. One should say that this, for instance, also shows us if I want to just compute what ij is, I can, if I can multiply it by k. So if I multiply this by k, I get
Minus k.
I get minus ij. No? So it's somehow it's so you get some relation that ijk is, if you permute them, then the sign changes in some way. So that ij is equal to minus ji and things like that. Okay. So, and one can check that this is. I haven't quite finished. So now one wants to see that this is a field, so we can have the analog of complex conjugation. Not a field, but a division ring. So if I have such a tuple, well, now do it the other way around, but anyway, EI plus CJ K can define the conjugate, and this is defined to be I change the sign of everything except for this one. So this is A minus PI minus CJ minus D. Okay. And then one finds that the inverse of an element, so if X is element in H without 0, then this can be written, so one can first see, maybe I should first say that, then first one sees if I take the product of X with its conjugate, if you just look at it, you now, the mixed terms kind of cancel out, and so therefore you find that this will be a real number. You just multiply this out, you see that no ijk survives. And you can define the inverse. The inverse with respect to this multiplication you can easily check is just the conjugate of x divided by x times the conjugate. And this makes this into a division ring. And so just to come back to briefly to the groups, we can look at a nice subgroup of H with respect to multiplication, which is a nice example of a non-commutative group. So this is usually called the quaternion group Q8, which is just the set of plus minus 1, plus minus I, plus minus j, and plus minus k. So these are altogether 8 elements with the multiplication. You can easily check that if you multiply any of these, you will stay inside the set. And this is an interesting non-commutative group. Of order 8. Now we had seen that if a group has as number of elements the square of the prime, it has to be commutative. But now we see if we have the third power of the prime, it can be non-abelian, and this is a if one, for instance, wanted to use the Seidel theorems to classify all groups of order 8, one would somehow have to find this group, and this would be, one of the reasons why it's slightly complicated. I mean, I just want to spell out again the axioms of the field, because this is, I mean, it's just a commutative division ring, but let me just spell it out so that we have it. So it means, so if I have a set K with two operations, plus and times, is a field if first we have two distinguished elements, 0 different from one element in K, and first, and then we have that R plus is a commutative ring with the neutral element 0. If I take R without 0 and take the multiplication, this is also a commutative ring with neutral element 1, and we have the compatibility, which is given by the distributive law. So if I take A times B plus C, is AB plus AC for all ABC. So you know that, but anyway, so just to remind us, it's given by two group structures which are connected by this distributive law. Okay, and we want to briefly see that there are also finite fields. So you know that whatever the rational numbers or real numbers or complex numbers are fields, we want also to see that there are some finite fields, namely, in fact, that we already have seen them, namely ZP for P prime number is a field. And for this we want to first see that if you have a finite integral domain, it's a field. It's actually quite simple. So if it's an integral domain, the only thing we have to see is that every non-zero element has an inverse. So maybe I call it R. So to show it has an inverse. Okay, so we have that if I take, we have seen that the distributive law says that if I take the multiplication by A from the right, from R to R, which sends A, say C to AC, this is a group homomorphism. For R with addition. It's a kind of trivial reformulation of this. And as R has no zero divisors, it means that this will send no element to 0 except for 0. So that means the kernel of R, kernel of this map is 0. So thus it follows that this multiplication map is injective. On the other hand, we have it's a map from a finite set to itself, so if it's injective, it's surjective. So it means, in particular, 1 is in the image, so shows that this element B in R with A times B is equal to 1. Okay. So that's quite simple. So in particular, we have this example, if P is a prime number, we know, we have seen that CP is an integral domain and thus a field. Normally, if one wants to think of it as a field, one denotes it as FP, because that's just Galois field order P. And so one could think that these are all finite fields, but that's not true. In fact, one can see that there are finite fields with p to the n elements for any power n. For any power p to the n of p. But that's all then. We will see that later. Okay, now to go on with the standard things. So we have defined rings. So we have to say what is a homomorphism of rings and what is a special property that the kernel of a homomorphism of rings has. For homomorphisms of groups, that's a normal subgroup, and here we have the analog, which is an ideal instead of just a subgroup. So, as before, for a homomorphism of groups, one had that it has to be compatible with the multiplication in the group, but here we have two operations, addition and multiplication, so it must be compatible with both. So the definition therefore is if A and B are rings, and a map phi from A to B is a ring homomorphism, I will write it out. If phi of A plus B equals phi of A plus phi of B, and phi of AB is equal to phi A times phi B for all AB. Okay. Obviously, we have the image, which is just phi of A. We have the kernel. Here one could think there are two choices, what could either, but we have here one distinguished element 0, and it's the inverse image of that. So the kernel is phi to the minus 1 is the kernel of phi. I mean, if A was a ring with 1, one could assume that one could take the inverse image of 1, but that's not a good idea. It's anyway not part of the story. In particular, we know that A is a group with addition, so this and this says it's a homomorphism of abelian groups for the addition. So therefore we know that the kernel is a subgroup of A, and we know that the kernel is 0 if and only if the map is injective. And that's certainly a useful thing. So mark so if B from A to B is a ring homomorphism, then if I take P as a map from A with addition to B with addition, this is a group homomorphism, is a homomorphism of groups, and so we know that thus phi is injective if and only if the kernel of phi is equal to 0. And that's obviously a very good thing that we again can check injectivity in such a simple way. And so one of the things that we will find in general is that the kernel of a ring homomorphism will always be an ideal. So like the kernel of a group homomorphism is a normal subgroup. And so it has a stronger structure than just being a subring, which I now introduce, namely an ideal. So a subset I in a ring of a ring R is an ideal, and I only consider two-sided ideals. So if you happen to know what that is, if first if I take I with addition, it's a subgroup of R, and we have one more condition for all say A in I and all X in R. We have AX is in I and XA is in I. So in order to be a subring, you would have the same condition where A and X are both supposed to be in I. But now we make the stronger condition that if I multiply an element in A with any element in the ring, I stay in the ideal. As we will see, this is important, for instance, if we want to take the quotient of R by I and want to make this into a ring. This condition will guarantee that then the multiplication will be well defined. Like the same as before when one had a normal subgroup in a group. There we had also some condition extra to being a subgroup, which then ensures that the multiplication in the quotient is well defined. So in particular, ideals are subrings. So it means clear that 0 and R are ideals in R, and if I have two ideals then the intersection is because we just make some assumption on every element in the ideal. So we just combine. So we can also, given some elements, we can look at the ideal generated by it. I only do this in the case when we have a commutative ring with 1. So that R be a commutative ring. So unity ring. They have some elements, A1 to AN, some elements in R. Then I can look at the ideal generated by these elements. So the ideal generated by C in R by A1 of AN is writing noted like this. And this is just all combination, linear combinations of these AI coefficients in R. So this means this can be formal sums A1 R1 plus AN Rn, all sums like that, where the these num R1 to Rn are elements in R. It's straightforward to see that this is an ideal. No, if I take sum of any two such, obviously it's an ideal, we just sum the coefficients, and if I multiply such a thing with an element in R, you just multiply these I with this element. And so obviously this is a smallest ideal in R containing all these elements. Because you can just take everybody 0 except for 1, and then you have the AI. And this is why I thought I wanted to have a commutative ring with 1, because it would seem strange to me to have the ideal generated by these elements which does not actually contain the elements. So but I mean, there's no real technical reason. So in particular, if we have an ideal which is generated by a single element, just A, which is after all just A times R, is called the principal ideal. And in fact, it's a bit where the name ideal comes from, because, so a principal ideal is basically, it's given by this element. But now, maybe sometimes sometimes the elements are not enough. You want some kind of ideal elements, and the ideal element is an ideal. I mean, it actually plays a role later when one talks about prime ideals. So I should have said this later, but anyway, I will repeat it when it fits better. So it's easy to see that if I have if R is an integral domain, then two such ideals, principal ideals, are equal if and only if these two elements are equal after multiplying by a unit. It is the unit U in R such that A is equal to U times B. It's kind of trivial if I don't. So if A is equal to U times B, then it follows obviously by definition that A is contained in B, but it's also true that B is equal to U to the minus 1A. But that must be the inverse. So we have that B is contained in A, and obviously all multiples of A are contained in this, so it follows that A is equal to B. And the converse is about as difficult, so maybe I leave it. So if these two are equal, you can easily find a unit. Okay, so what else did I want? Yeah, now I want to say this thing that the kernel of the ring homomorphism is an ideal, and then in case, it turns out in case the ring homomorphism is surjective, then also so now let me of course go back. The kernel of a ring homomorphism is an ideal, and more generally the inverse image of any ideal is an ideal. And if the ring homomorphism is surjective, we also have a converse, namely the image of an ideal would also be an ideal. But that's only if it's surjective, otherwise not. Now, in particular, the image of the whole thing, the image of the map is only a subring, therefore not an ideal, but obviously the surjective is the whole thing, and therefore an ideal. So this is the following lemma. But the most important thing is somehow that the kernel is an ideal. So let P from A to B be a ring homomorphism. Then first, the kernel of P is an ideal in A, and more generally, we have that for any ideal I in B, we have that phi to the minus 1 is an ideal in A. Obviously, the first statement follows from the second because 0 is an ideal, and so the kernel is its inverse image, and so therefore it's an ideal. So we will only have to show the second statement. And the other one is, as I said, assume phi from A to B is surjective, then here I see it like that. The map from the ideals in B, so the ideals in A, which contain the kernel, which sends an idea to its inverse image, is a bijection. And in the course of the proof of the second one, we will also show that the image of an ideal, if the map is surjective, the image of an ideal is an ideal. That is necessary to show that this is a bijection. The first one is anyway more important and easier. So first, so let say J be an ideal in B. So we want to show that its inverse summation is an ideal. So clearly, phi to the minus 1 of J is the subgroup of A with the addition that we know. So now let A be phi to the minus 1 of J, and okay, that means phi of A is in J. Then with X in A, then if I take phi of, say, XA, this is equal to phi of X times phi of A, and as this one is in J, and as this is an ideal, this is in J. So it follows that XA is an element in phi to the minus 1 of J. And in the same way, AX is in phi to the minus 1 of J. So it follows it's an ideal. All follows quite directly from the definition. Now we want to prove the second one. So let much time? Oh, there's still a lot of time. Let J be an ideal in B. So by the first part, we have phi to the minus 1 of J is an ideal in A. And clearly, phi to the minus 1 of J contains phi to the minus 1 of 0, which is the kernel of phi. So we see that this map is at least well defined. It sends any ideal in B to an ideal in A containing the kernel. I want to show it's a bijection. We want to give the inverse map. And the inverse map is just by taking the image. So I look at the ideals in A containing kernel P. To the ideals in B, and I send I to P of I. Actually, I don't really need that to have this make sense. I don't need that it contains the kernel of P. But anyway, so I want to see that this is that this makes sense. So this is an ideal, and secondly, that it's the inverse. So phi of I is an ideal in B. So again, obviously, if I take phi of I with the addition, it's a subgroup. We only have to show this idea problem. So let y equal to phi of x be an element in phi of I, and say b equal to phi of a be an element in B. Here we use that the map is surjective. So where x is in I and A is in A. Then it follows that AX is in I and XA is in I, and so thus YB equal to phi of AX is in phi of I, and EY equal to phi of I know what we wrong with wrong, but anyway, so this is XA of AX is in phi. So this is an idea. So all is just now we want to show it's this map is the inverse. So clearly, if J is an ideal in B, then if I take phi of phi to the minus 1 of J, this is J. And for any subset, this is the case. So we see that in this direction, if I first apply this phi to the minus 1, then phi, this is the identity, so the inverse. Now I have to show that the other composition is also the identity. So finally, let I in ideal in A, which contains the stupid thing, yeah. With A contains kernel of phi. What? Yeah, okay. Then what? So we want to show, so we have to show that if you take phi to the minus 1 of phi of I, this is equal to I. Obviously we have the inclusion, and clearly I is contained in phi to the minus 1 of phi of I. No? The things which map to the same thing as I, no, this contains among those is everywhere in I. So we have to show the other inclusion. So let Z be an element in phi to the minus 1 of phi of I. We have to show it's in I. So then phi of Z is in I. That's the definition. Yeah, it's not an I, in phi of I. So that means there is an element in I which is sent to the same element. Of Y. So that means that, which we wanted, phi of Z minus Y is equal to 0, so that means Z minus Y is in the kernel of phi. And in particular, it lies in I. And so therefore, if we look at Z, I can write this as Y plus Z minus Y. This is an element in I, and this also is an element in I. And so this is an element in I. And so our element Z was already in I. So it's not, it's all maybe a bit too elementary, but okay. That's that. Let me see whether there's something I can make this simple application. Okay, so I make some other simple remark, which will be useful. Just some simple fact. So, if an idea contains a unit, it's the whole of the ring. I in ring R in idea if I contains a unit, then I is equal to. Okay, well, second one is application of that. So if let K be a field, the only ideals in K are 0 and K. If we have a field, it has extremely few ideals, and the consequence of that will be that if I have a homomorphism from a field to another ring, then it's either injective or the zero map. So that K be field, P from K to R, where R is a ring. The ring homomorphism, and it follows phi is injective or phi is equal to 0. So, and now obviously this is not such a complicated thing, it's all a restatement of the same simple observation. So if, let's assume, so this is only proof 1, let's assume we have an element A which lies in the ideal and is also a unit. Then also its inverse, so then you can multiply the inverse, so 1, which is equal to a to the minus 1 times a, is also an element in I. And so if B is an element in R, then B equal to B times 1 is in R. So just by definition, once it contains a unit, it contains everything. And the second statement is just the reformulation, because if I take the units of K, this is equal to K without 0. No? And so if an idea contains an element which is not 0, then it must be the whole of K, according to the first part. And the third one is just that we know that the kernel of phi is an idea. So the kernel of phi must be either equal to 0, that the map is injective, or it must be the whole of the field, so then the map is a 0. Okay, maybe I will stop here if there are no questions.